Alrighty, let's see, where were we? We were reviewing Fourier series, and as our example, we were looking at the Fourier series of a square wave, 50% duty cycle pulse. We had it going between 0 and 1. And we saw that the Fourier series for this, the DC term, was 1/2. We computed that using L'Hopital's rule and on the AKs where you plug in k equals 0. And we also used a trick of just directly computing the quote-unquote DC value, the average value of the wave, and found that these are the same 1/2. As a little aside, there was a little bit of a strangeness when we computed AK for k equals 0 by writing something where they took the limit as k goes to 0. And that should make you a little queasy because k is really an integer. So for k to be a small number going to 0 but not quite 0 is a little strange, but, you know, we're all friends here. So if we look at for the AKs that aren't the special case, we wound up with a form that looked like sine k over 2. No. Yeah, let me write this as pi over 2k. Just looks a little better, I think. So write this pi over 2 times k. So this is a big K times the whole thing. And we've got pi k sitting here in the denominator. And what we can do is let's write a line here that we'll use to graph the spectrum of this. And I'll put 0 here. And here I'll put omega naught. Here I'll put omega, no, actually, yeah, that's omega naught. And this is 2 omega naught. This is 3 omega naught. 4 omega naught. This is getting a bit tedious, but you get the idea. Here's 5 omega naught. This is not awesomely to scale. Same thing on the other end. I've got minus omega naught, minus 2 omega naught, minus 3 omega naught, minus 4 omega naught, minus 5, da 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 da. So I've written a frequency axis that's in terms of radians per second or whatever your time unit is. And what we'll do is we'll draw little arrows to indicate the Fourier series coefficients. So for A naught, let me draw one in here. We'll label this 1/2. Draw a little arrow there. Well, what about these others? Well, for any of the even ones here, 2 omega naught, 4 omega naught, the 2 minus omega naught, the minus 4 omega naught, for all of those, this numerator is 0. So we're essentially missing those harmonics. And this is something you perceive in the tone compared to something like a sawtooth wave that has a very buzzy quality to it. That's something used to music synthesis to create trumpet-like sounds. A square wave has more of a hollow clarinet-like sound from these missing harmonics. So those are all zeros. Well, what about the others? Well, say for k equals 1, this sine pi over 2 is 1, and this is 1 divided by pi. So it's around 1/3. So maybe I'll draw something like this. Again, this is not awesomely to scale. And now what about over here? Well, if I plug in minus 1, the sine minus pi over 2, that will give me a minus 1. But if I'm plugging in k equals minus 1, those cancel. So in this particular case, this guy is symmetric. So I'll get this 1/3. And we'll come back to the symmetry question in a little bit. The fact that we see the symmetry here has to do with the way we originally defined our wave as being centered at 0. So it was symmetric around 0, and that gives it a certain kind of symmetry in the Fourier series coefficients. We'll talk about more kinds of symmetries later. What about the other things here? So the pi, the sine 3 pi over 2, that gives me a minus 1. And that would be divided by, let's see, so that's this guy here. Oh, it's not 1/3. Sorry, it's 1 over pi. I was just using 1 over 3rd as a way of trying to figure out how far to make this line. And I probably failed at that fairly miserably, but anyway, okay, so this is 1 over pi. Pi third, so it would be kind of a third of that. So this wasn't really exactly a third. It's really 1 over 3.14. But let's say we'll look something like, whoop, I'm putting it in the wrong spot. It's over here at 3, and it goes downward. So this is like minus 1 over 3 pi. Same thing over here. So this guy's going minus 1 over 3 pi. And, well, what about 5? Well, then it flips back around. So it's going 1 minus 1, and that's 1 over pi fifth. So I'll write this little guy there. 1 over 5 pi. Same thing over here. Happens to be symmetric. 1 over 5 pi. Like that. And it alternates sign like that. It goes 1, minus 1, 1, minus 1. Or, no, I should say it goes plus, minus for this particular example. Same thing on the other side. Only on the odd harmonics, so it's skipping the even ones. So other kinds of waves might have even harmonics. So a few comments on this particular chart. One is, notice we're using arrows here. If you are a Georgia Tech ECE student, you probably took either ECE2025 or ECE2026 is sort of the newer incarnation of that class, where we used arrows in the spectra. But back in 2025 or 2026, we didn't really tell you very much why those are arrows. These arrows are used to represent the Dirac delta functions, which at Georgia Tech we're now introducing, in the ECE department, we're introducing those in ECE3084. They used to be introduced in the predecessor to 2026 and 3084. There was an old class called 2025 that I taught for a good decade, I think, where we use arrows to represent these Dirac delta functions. Now, to complete, quote-unquote, the loop on this, using that term broadly, I'm not talking about feedback control or anything, just a little bit later in the class we'll be looking at Fourier transforms, which are kind of a more general version of the same idea underlying Fourier series. Those Fourier transforms are going to have 2 pi's sitting in front of here that we're just going to have to add in. It's confusing. It's something that we tried to figure out how to teach in 2025 and 2026 and not be confusing. If we put in 2 pi's back then, we would confuse people because we would just have to say, trust us, these are supposed to be there. But right now, this is writing the spectrum in the terms of sort of the style as the textbook for ECE 2026 at Georgia Tech. Later, when we do Fourier transforms, we'll introduce these 2 pi's that sit out in front of these terms, in front of the Fourier series coefficients. We'll get to that when we get to Fourier series, but for right now, this is just A0, this is A1, what's down here? This is A3, this is A5, this is a -1 on the other hand, and so on. The other important caveat here in looking at this plot is that in this particular example, all of the Fourier series coefficients were positive or negative real numbers. In general, the AKs are complex valued. So in this particular case, it made sense for me to plot these things as going positive or negative. Similarly, let's say you're in a case where the AKs were purely imaginary. You might do a similar plot going plus or minus, going up and down this, but you might have J's here. You'll have a J, and things could go plus or minus in some way. In that case, it kind of makes sense to make a plot like this. But for more general complex valued AKs, those AKs have a magnitude and a phase. In this particular case we're seeing here, the phases, you can think of them as all being 0 for the positive going ones, or pi, or equivalently minus pi for the negative going ones. But in general, they might be something like, you might have 3 e to the j pi over 6. So if you have that e to the j pi over 6, how would you draw that this way? And the answer is you really can't. You would have to have some sort of 3D plot where you have frequency going on one axis, real part going along another, and the imaginary part going on a third-dimensional axis, coming into or out of the chalkboard or the dry erase board or your computer screen in this case. Given you now have a good sample of my artistic skills, you'll very quickly realize it's not a good idea for me to try to draw something like that. So it's generally done usually when drawing these kinds of spectral plots for these Fourier series coefficients, or even for Fourier transforms when we get to those later. Quite often what you do is you'll make a separate plot for the magnitude and the phase. Now you could also make one plot for the real part and another plot for the imaginary part, but it's quite often very difficult to interpret what that means. It's usually a lot more sensible to make a plot where you plot the magnitude and a separate one for the phase. So for a magnitude plot, you might see something like this, where everything's just going up, because we're just plotting the magnitude of these things. So here's a little one, and something like that, and so on. Remember this formula that we computed for the AK, unlike some of the first examples we looked at earlier, for this example where we have a square wave, there's big discontinuities in that. There's a big jump. And so that's going to have a Fourier series that has coefficients that, go out to infinity. Now they drop off pretty fast. They're dropping as 1 over k. And that has to do with the fact that you've got a certain kind of discontinuity. Depending on the discontinuities you have, you'll get different kinds of roll-offs. For example, just as an aside, if you have a triangle wave, that doesn't have standard calculus-style defined derivatives at these points, although it is continuous. Now, of course, with unit steps and impulses and things, we can talk about taking derivatives and things like this. But in, actually, you can take the derivative or something like this. Sorry, it would turn into a square wave. So the actual original triangle wave is continuous, but its derivative isn't. Whereas here, we're actually computing the Fourier series coefficients for a square wave. So that has a certain slope pattern. But if we computed the Fourier series coefficients for this triangle wave, you'll see that they instead slope off of an order of something like 1 over k. So for the, 1 over k squared. So they slope faster. So for something like this, it's on order 1 over k, how these things slope off, using a computer sciencey kind of way of thinking about it. For this triangle wave, if we sat down and slogged through that, you'll see that they slope off as like 1 over k squared in terms as an order. So they slope off a lot faster. So this triangle wave, it has a very mellow sound compared to the square wave, or definitely compared to a sawtooth wave. People in doing music synthesis, they're using square waves for clarinets. They'll use something like this triangle wave as the basis for a flute. It's just a much more mellow sound. It has a lot more of the fundamental relative to this higher order harmonics. So we'll make plots along these lines. And so the final thing we'll look at next time is what happens when we put one of these periodic signals through a filter. And so we'll talk about that next time.